Electricity demand will triple over the next 2 decades, driven by electrification of everything from cars to cooktops. Even without climate pressures, the dramatic decrease in the cost of renewable power generation makes it just the cheapest source of electricity to satisfy the increasing demand. But renewables are less predictable and more geographically spread than traditional power plant generation. With more demand and less predictable supply, power grids around the world are becoming congested and less reliable. Grid operators are quite literally struggling to keep the lights on and need to find a better way. Hello, my name is Paul Reed. I lead sustainability and clean energy at AWS Industry Products. And my teams are working closely with utilities and grid operators around the world to help them transition to clean energy by building new technologies and innovating on AWS. In the next 20 minutes, I'd like to talk to you about some of the problems and some of the customers and the solutions that we're building. At AWS, we're committed to supporting a sustainable future. A little over 5 years ago, Amazon co-founded and was the first signatory of the Climate Pledge, which calls on companies to commit to reaching net zero carbon emissions by 2040, 10 years ahead of the Paris Agreement. Amazon continues to reduce emissions across our operations to address the urgency of climate change, as well as encouraging other companies to join in signing the pledge to accelerate their goals, plans, and programs. Transitioning to carbon-free energy is one of the highest impact ways we can reduce emissions in the near term. In 2023, Amazon was the world's largest corporate purchaser of renewable energy for the 4th year in a row. And 100% of the electricity consumed by Amazon was attributable to renewable energy sources. That includes the electricity used by our AWS data centers. As of January 2024, Amazon has over 500 renewable energy projects. To put that in context, that represents 28 gigawatts of clean energy capacity, or nearly 77,000 gigawatt hours, which is enough clean energy to power 7.3 million US homes or 20 million European homes for an entire year. With increasing focus on renewable energy by both consumers and corporations, and the growth of distributed energy resources such as EVs, solar panels, and batteries, utilities face rapid changes in the patterns of supply and demand on the power grid. The International Energy Agency estimates renewable generation will nearly double in the next 5 years. And Wood Mackenzie estimate in the US, over 1/4 terawatt of new DERs will come online in the next 3 years. And while this might sound like a lot, at the same time, McKinsey note that delays navigating the complex, decentralized process of connecting to the grid is holding us back, impacting the financial viability of renewable energy projects, making them less attractive to developers, and ultimately slowing our transition to carbon-free energy. Meanwhile, the US Energy Information Administration note that the grid we have today is less reliable, with more outages happening more frequently, creating more disruption. Traditional approaches to planning, operating, and maintaining and expanding the grid just no longer work. The one-way flows that we're used to of power coming from generation to consumption that have been the norm for decades are being replaced with distributed generation, local storage, and bidirectional energy flows. Simply put, our power grid was not built for the world we're moving into. So to handle the dynamic nature of today's supply and demand for power, and to accelerate the transition to carbon-free energy, we believe grids need to move from being hardware-defined to being software-defined. A software-defined or dynamic grid is one where real-time data drives insights and scenario planning so that grid operations can be optimized continuously. This starts at simplifying and greatly speeding up interconnection, the process of connecting new things to the electricity grid. Holistically analyzing excuse me, holistically analyzing the grid at multiple levels from high voltage distribution to low voltage transmission. Leveraging real-time data to proactively optimize performance of existing infrastructure, and putting business logic close to data to reduce latency and increase reliability. At AWS, we know data, we know analytics, we know optimization, and we can do all three at scale, cost-effectively, reliably, safely, and securely. Let's look at three key challenges that utilities face in achieving this dynamic grid vision. First, grids are made up of millions of physical assets: poles, wires, switches, transformers, power stations, all connected to form what we refer to as the grid. But this collection of interconnected assets has grown and evolved over many decades. And the assets are often owned and managed by different parts of the utility or even the local municipality in which the utility operates. There isn't a single source of truth that can be relied upon for how the physical grid looks or is being operated today. This leaves utilities trying to plan improvements or make operational changes based on inaccurate or outdated information, leading to delays, increased costs, and unreliable delivery of power. Next, we'll look at simulation at scale. Power flows around the grid based on the laws of physics. Utilities want to be able to study the impact of new loads such as EVs or new data centers, or the cost and benefit of connecting a wind or a solar farm at a certain point on the grid, or how to plan for or respond to weather events such as hurricanes and tornadoes. Simulating how power will flow around the grid in the face of planned or unplanned real-world changes is critical. Simulating how power will flow around the grid in the face of planned or unplanned changes is critical to being able to reliably and safely operate and plan for expansion of the grid. Lastly, we'll get to this one now. Lastly, electricity meters such as the ones on your or my house form the edge of the grid, tracking power usage and quality at the point of consumption. Existing meter data systems were built for the purpose of billing customers once a month, often referred to as meter to cash. But with access to higher frequency data from smart meters, we can unlock insights in real time to optimize demand and supply. We can inform generation capacity and curb or time shift loads to shape demand, making optimal use of the available sources of renewable power and relying less on ramping up and down traditional carbon-intensive generation. To address these three challenges, let's look at some of the work my teams are doing with customers today. Duke Energy, one of the largest energy holding companies in the US, has been an AWS customer for many years. We've had a development collaboration with them since 2022. Through this collaboration, my team are building new technologies in AWS to support Duke and utilities like Duke on their transition to clean energy, helping to analyze demand, forecast loads, and recommend grid improvements through operations and capital investment. For example, adding a residential solar or commercial scale EV chargers to a distribution feeder requires Duke to conduct power flow calculations, and these calculations are complex, modeling voltages, voltage angles, real power and reactive power. It's really complicated stuff when you get into it. Existing on-premises tools, however, are too slow, or because of the complexities, only analyze a narrow subset of the grid. Working closely with Duke, we've developed a solution that can cost-effectively run hundreds of millions of these grid simulations at scale. We've been able to run power flow simulations in 15 minutes on AWS that previously took Duke 6 weeks on premises. 15 minutes, 6 weeks. Big improvement. Vector are a New Zealand energy company who run a portfolio of businesses delivering energy and communication services across Australasia and the Pacific. We've had a development collaboration with them since 2021. I happen to live down in Wellington. Vector were eager to leverage this high-frequency data coming from smart electricity meters that I mentioned earlier. While metadata has traditionally been used for billing, regulatory changes in Australia required measuring consumption at 5-minute intervals. Not daily, 5-minute intervals. And Vector wanted to be able to leverage this higher frequency, higher fidelity data to offer their customers richer insights to help meet their decarbonization goals. Working with existing services and new technologies developed by my team, Vector have built Diverge, a cloud-native energy data platform that collects and analyzes metadata at scale. Today, Vector have over 1 million smart meters in Australia and New Zealand. Don't know why it keeps doing that. Today, Vector have over 1 million smart meters in Australia and New Zealand running on Diverge. They're processing 6 times the data, 10 times faster than their previous legacy metadata management system. Moving from custom work to some research work that we've been doing, Pacific Northwest National Labs, one of the US Department of Energy's national research laboratories, wanted to study the adoption of residential solar and EVs over the next 30 years to understand where and when grid bottlenecks might occur. Traditional approach to this sort of problem would be to analyze peak scenarios for a subset of the years over the time frame of the study. The plot on the left here shows the results of that sort of traditional analysis. What PNNL did was to use AWS to perform a stochastic analysis running nearly 9,000 power flows for the next 30 years for each of the 500 trials in question, for a total of 131 million power flow simulations. All of this ran in less than an hour on AWS, and the plot on the right shows the results. As you'll see, the location and severity of grid bottlenecks found through this second approach are quite different, and using these sorts of results could help utilities target very different investments in upgrades to support these expected future loads. And these three are just some of the areas that AWS are helping customers and partners. Reducing carbon emissions requires shifting to renewable energy, increasing electrification, and planning and operating a more dynamic power grid. This shift to a dynamic grid requires electric utilities to analyze vast volumes and scenarios, accounting for uncertainties in weather, EV adoption, distributed energy resource adoption, and more. My teams are working with utilities and labs around the world to identify applications and technologies at the heart of transforming the power grid and accelerating our transition to a carbon-free renewable energy. Together with these customers, at AWS, we're building, testing, and proving out the key enabling technologies that make the dynamic grid a reality. My team have a demo over here, just 2 minutes away. If anybody wants to look at more details, thank you for coming. I'm available for questions off mic, and hope the rest of your reInvent goes well.